Welcome to Numerical Methods for Scientists and Engineers. Video number 6. Ill-conditioned matrices or ill-conditioned linear systems. In linear algebra, the term ill-conditioned or ill-conditioned typically refers to a situation where a mathematical problem, particularly one involving matrices, is sensitive to small changes in the input data. This term is often used specifically in the context of solving systems of linear equations, matrix inversion, or numerical methods. A matrix is said to be ill-conditioned if its condition number is large. A well-conditioned problem is one in which a small change in any of the numerical data causes only a small change in the solution of the problem. An ill-conditioned problem is one in which a small change in any of the numerical data causes a large change in the solution of the problem. Condition number, kappa A, is used as a measure of the sensitivity of a matrix or a linear system to small changes, errors, or perturbations in any one of its elements, and it is defined in terms of norms as follows. The general family of p-norms, or LP norms, is defined as follows. Specifically, the L1, L2, and L-infinity norms of a vector x can be calculated as shown. L1 norm denotes the total magnitude of a vector. L2 norm denotes the shortest distance between 2 points in Euclidean space. The L-infinity norm denotes the sum of the lengths of the vectors in a space. The two matrix norms commonly encountered are the L1 norm, maximum column sum, and the L-infinity norm, maximum row sum. The L2 norm of a matrix A, also called the spectral norm, is defined in terms of the maximum eigenvalue of the matrix product A transpose A as follows. The LF norm of a matrix A, also called the Frobenius norm, is defined as follows. Condition number, kappa A, is used as a measure of the sensitivity of a matrix or system to small changes, errors, or perturbations in any one of its elements. It indicates how much the output, that is, solution, of a linear system can change relative to small perturbations in the coefficient matrix or the right-hand side vector. It is important in numerical analysis because it gives us an idea of how stable or unstable the matrix is for solving systems, and it is defined as follows. Condition number depends on the type of the norm, indicated by the corresponding subscript as 1, 2, f, or infinity. Each condition number type provides a different perspective on the stability and sensitivity of a matrix problem, and the choice of norm depends on the specific application or problem being solved. Calculating condition number can be computationally very expensive. Calculating the inverse of the matrix can also be problematic due to the complexity of matrix inversion, which requires on the order of n-cube operations for an n times n matrix. The calculation can be further exacerbated by the need to compute the matrix's largest and smallest singular values. The L2 norm of a symmetric matrix requires the computation of the maximum eigenvalue. If a matrix is ill-conditioned, the computed condition number of the matrix will be unreliable and can differ by many orders of magnitude. An upper bound estimate for the spectral condition number for a matrix A can be obtained as follows. The condition number can be best estimated if the matrix is equilibrated. That is, the rows of the original matrix are all normalized to have elements with a maximum magnitude of order 1 or transform each row of the matrix to a unit vector in Euclidean norm. The spectral condition number for the equilibrated matrix M yields the following. Numerical estimates for the condition number can be improved while solving the system of equations. Let us consider the linear system AX equals B whose solution is Z. Owing to properties of the norms, we may write, which provides an upper bound for the norm of the inverse of the matrix A. Solving two systems of equations, transpose AB equals U and AZ equals B. An estimate for the condition number is proposed as the condition number of the coefficient matrix of a large system of equations should be computed, or the problem should be, if possible, reformulated to avoid ill conditioning. Nevertheless, it should be noted that a system of linear equations obtained as a result of implementing numerical methods to ordinary differential equations or partial differential equations is not ill-conditioned. The ill conditioning is most severe in linear systems arising from least squares regressions. Contrary to theoretical expectations, using digital computers in computations with ill-conditioned matrices does not produce a true solution even if direct solution methods are used. Performing high-precision arithmetic reduces the round-off errors and helps mitigate the major adverse effects of ill conditioning. Consider the following 3 by 3 matrix. Its determinant is 4.9 times 10 to the power of minus 7. A small determinant of a matrix suggests that the matrix is close to being singular, and the matrix is likely ill-conditioned. However, the condition number is a more direct and precise measure of ill-conditioning than the determinant. In this exercise, we will calculate all possible condition numbers for the given matrix A. But first we will calculate the different types of norms, which are necessary for calculating the condition number. The infinity norm of the matrix A is the maximum absolute row sum of the matrix, which is observed to occur at the first row. The L1 norm of the matrix A is the maximum absolute column sum of the matrix, which is observed to occur in the first column. The Frobenius norm of a matrix A is the square root of the sum of the squares of all of the entries in the matrix, which for matrix A yields 1.31227. The L2 norm, or the spectral norm, of a symmetric matrix is the maximum magnitude eigenvalue. And the characteristic equation of the matrix A is a cubic polynomial, whose roots are real numbers. And the maximum magnitude eigenvalue is 1.31227. The numerical accuracy of the condition number computed by the definition clearly depends on how accurately its inverse is computed. In the following calculations, the inverse matrix is computed using very high precision to reduce the effects of ill conditioning. The condition number based on L1 and L infinity norms are the same due to symmetry of the matrix A. Frobenius norm is smaller in magnitude, and spectral norm is found as 2811.95, which is the smallest of the computed condition numbers. If a matrix is severely ill-conditioned, estimating the condition number by evaluating the inverse matrix not only increases the computational cost significantly, but also raises questions regarding the accuracy of the result. Consequently, we should not use the numerical value of the condition number that is not reliable. A matrix that has been transformed or scaled in such a way that the row and column sums, or norms, are more balanced, or equilibrated. This can be done by applying a scaling transformation that makes the matrix more stable for numerical computations or optimization. In practical terms, Equilibration typically involves scaling the rows and/or columns of a matrix to improve the numerical behavior of a matrix, particularly in solving linear systems or eigenvalue problems. The given matrix is equilibrated by transforming each row of the matrix into a unit vector in Euclidean norm, which leads to the spectral condition number based on matrix A is estimated as, which is 1.775 million. On the other hand, spectral condition number estimate based on the equilibrated matrix M is smaller than that based on matrix A. These estimates provide an upper bound for the condition number. Another estimation requires solving two systems. Transpose AB equals U and AZ equals B. Solving a transpose X equals B yields. We then calculate L1, L2, and L infinity norms of vector B as follows. Next, we solve the matrix equation AZ equals B using high-precision computation. Likewise, we calculate L1, L2, and L infinity norms of vector Z. Now we obtain 1, 2, and infinity base condition numbers as follows. These estimates are closer to the true condition number values. Now let us consider the following linear system of equations, whose true solution is given as follows. We introduce a small perturbation to the second and third elements of the right-hand side vector. We obtain the solution using double precision to yield the following, which is significantly different than the true solution. Next, we consider another perturbed linear system. The solution deteriorates. Now we invert the matrix using single precision computation. Furthermore, we will round the numerical values to 3 decimal places as shown below. The multiplication of the matrix with its inverse should yield the identity matrix. However, the matrix identity A times A inverse minus I equals 0 matrix is not exactly satisfied. Inverting matrix A twice should also yield matrix A. This identity, too, is not exactly satisfied, which depicts the effect of ill condition. That is all for now. See you next time with another topic. Bye.